Hello, everyone. My name is Yuexing, an assistant professor at Johns Hopkins Carey Business School. I'm very delighted to present our paper, Data-Driven Clustering and Feature-Based Retail Electricity Pricing with Smart Meters. This is a joint work with Professor Bora Kesking from Duke University and Professor Noor Sunar from UNC Chapel Hill. This paper is motivated by a real-life smart meter dataset from a major US utility company. A smart meter is an electronic device that records electricity consumption in real time, enabling two-way communications between the utility provider and the end users. They can also communicate price signals, improving transparency of the pricing plan. We observe multiple types of information in this dataset. The first type is the weather information around a neighborhood, which varies over time, but is the same for all users in the same neighborhood. Besides that, audits and surveys provide rich information about house construction, such as the foundation type and square footage, and various electronic devices owned by households. They vary over users, but do not typically change over time. We call all such information altogether collectively as features. Most importantly, smart meters provide highly granular data on customer consumption patterns. We're going to use all these data to uncover any customer segmentation and learn the effect of price and features on electricity consumption. Before delving into the detail, let me provide you a high-level overview of the main contributions in this paper. To the best of our knowledge, this is the first paper to analyze data-driven joint clustering and contextual dynamic pricing. Based on the observations from the real-life dataset, we are the first to formulate a general model that encapsulates three different types of features: time heterogeneous features that vary only over time, such as weather; user heterogeneous features that vary only over users, such as the square footage of the house; and fully heterogeneous features that vary both over time and users, such as the user consumption profiles. The challenge of having all three types of features together is that they jointly do not form an IID sequence. We developed a new method called the parallel partial regression to overcome this challenge. We then derive distinct theoretical results to identify how different forms of feature heterogeneity influence the policy performance. And finally, we conduct a case study using the real-life smart meter data. The results indicate that our policy increases the company's profits considerably. We also show that our policy is robust to various forms of model misspecification. Now it's time to take a look at how we formulate the problem into a mathematical framework. We consider a utility provider called the seller serving end users over T periods. At the beginning of each period, the seller observes a high-dimensional feature for each user I. This feature contains three components: the time heterogeneous features, the user heterogeneous features, and also the fully heterogeneous features. These three types of features altogether induce a cluster structure given by the function C that maps any feature to its cluster label. The seller does not know this function C and needs to learn it using data. Upon observing a feature in time t for each user I, the seller sets the price and observes the corresponding consumption according to this generalized linear model with a link function g. The consumption parameters include the baseline consumption parameter, the feature coefficient, and also the price sensitivities. They're all unknown to the seller and must be learned using data. To overcome the challenges due to unknown information and various types of features, we designed a data-driven clustering and feature-based pricing policy as follows. We first dedicate certain periods for price experimentation and use that information to estimate the cluster structure and the corresponding consumption parameters in each cluster. We then perform cluster update, predict the cluster of the new features, and then set the price for profit maximization. We measure the performance of our policy using the average regret over all periods and all users relative to a clairvoyant who knows all the relevant information. We derive distinct theoretical results to show that our policy achieves the best achievable upper bounds on regret that goes to zero according to these rates. Well, this means that if you are implementing our policy for a longer period of time and more users, your profit will be getting closer and closer to the clairvoyant optimal policy. To see how our policy performs in a particular real-life setting, we conduct an extensive case study based on the real-life dataset. As mentioned earlier, we have smart meter data of electricity consumptions in a neighborhood in Austin, Texas, audits and surveys such as the demographics and even some comments in text, as well as some weather information. We then use the natural language processing tools to convert the text into predictors and obtain 157 features in total. We then calibrate the model using a 3-month period data as a test bed, where each period corresponds to 1 hour. The left figure illustrates the cumulative profits over this 3-month period, and the bar chart on the right shows the total profits by the end of the 3-month period. Our policy significantly outperforms the company policy by more than doubling the company's profit. We also compare our policy with alternative heuristics that lack certain elements in design. This table shows 2 snapshots of the percentage increase in average regret if we replace our policy with the corresponding variance, which all perform worse than our policy. This demonstrates that all design elements of our policy are indispensable. Once again, these are the highlights and takeaways of our study. Thank you so much for your attention. I'm happy to answer any questions you have.